In the previous video, we used ray diagram to help us determine the characteristics of an image, knowing that we know the distance of the object from the vertex of the mirror and we know the height of the object. So that question actually leads us to the conclusion that by using ray diagram, if we know the object's height and its distance from the vertex of the convex or concave mirror, any kind of mirror, we are able to determine the characteristics of the image, whether it being real or virtual, whether it being upright or inverted, or magnified or diminished. So these are the characteristics. We call it the nature of the image, the orientation of the image, and the size of the image. Okay, so yes, those things are good. It's very helpful for us to determine the characteristics. But what if today I want things to be a bit more precise? And when you say magnified, I want to know magnified by how much. If my object here is 1 meter, what will be the size of the image that is formed by this concave lens, a concave mirror? So I want to know the exact measurements. How far is it away from the vertex of this concave mirror over here? So if you want things to be exact, well, ray diagram will not be a good option now. Ray diagram, of course, if you draw everything to be very, very precise, you use your compasses, you use your protractor to determine everything nicely, you are able to determine the size of the image by measuring the height over here. It's possible, but it's so tedious. We actually have a better way of getting around the situation by moving on to talk things in terms of equations. Now we'll try to get mathematical a bit. From graphical approach, we try to move on to a mathematical approach by using the mirror equation and the magnification. Okay, this red box over here contains the mirror equation, whereas this red box over here contains the magnification. Sometimes we also call it the lateral magnification. It depends on which book you follow. Okay, so these two equations here relate between the characteristics of the objects, such as the object's distance, or the object height, and you relate it with the characteristics of the image, such as the image distance, or the height of the image. Well, to relate these two things together, we need to know clearly the characteristics of the concave or convex mirror. So for the characteristics of the mirror, we will represent it with this value here called the focal length. Okay, so the focal length, I hope you haven't forget it yet, but focal length is the distance between the focal point and the vertex of the mirror. So in this case, for mirrors, we know that the focal point will be the midpoint between the center of curvature and the vertex of the concave or convex mirror. So the center here will be the focal point, and if we measure the distance from the focal point to the vertex, we will obtain the focal length of the mirror itself. So object distance, I think it's quite easy. You just measure from the arrow to the vertex. Then the image, you measure from the image arrow to the vertex. So what is the purpose of these equations here? These equations here actually allow us to deduce the characteristic of the image by knowing the characteristic of the object and the characteristic of our mirror. So if we know what mirror are we using, and we know how far do we place our object, we are able to determine how far away is our image. And this equation here actually relates the image and object distance. You relate it to the height of the image or the object. So basically, these two equations here, both of them together will function to determine the characteristic of the image in terms of numbers, concrete numbers. Okay, it's easier to use the equation compared to drawing all these rays and straight lines and curves. But the problem of using equation is you have to be very, very careful, extra careful actually, when you're dealing with equations in chapter 7. For chapter 7, even though let's say object distance here, you measure it to be 5 cm, but you can't just substitute 5 cm to represent the u. For all the u, v, and f over here, they need to carry sign. They need to carry either positive sign or negative sign. let's say if I measure the focal length to be 5 cm, so it's not accurate enough to just say the focal length is 5 cm. If you want to substitute f here, you have to know whether it's negative 5 cm or positive 5 cm. If you want to put in the u to be 10 cm, let's say, you need to know whether it's positive or negative 10 cm. So all these u, v, and f here carry sign in front of it, and the sign can be determined by this sign convention over here. So it's very important for you to be very clear about the sign convention, because you'll be carrying this sign convention throughout the whole chapter 7. Okay, so for object distance, which is the distance of this arrow representing object to the vertex of the mirror, if your object is on the same side as the incident ray, then your u will be positive. So let's say if I measure this u to be 10 cm, now let's check whether it should be positive or negative. Well, our incident ray is coming here. Okay, so our incident ray is actually in front of the concave mirror. We call this portion here in front, and behind this opaque surface, we call this behind the mirror. Okay, so you can see that the incident ray is in front of the mirror, then object is also in front of the mirror. So both of them are at the same side of the mirror. Okay, so in that case, we can know that the object distance here should be positive. Okay, well, for most of the case that I can imagine in my head now, the u is usually positive. As you can't imagine a situation where the object should be on the opposite side of the incident ray. I haven't really figured out is it possible or not. But for many of the case, probably all of the cases, your object should be on the same side as the incident ray. So u is most probably positive. Okay, so if in this case 10 cm, I need to substitute positive 10 cm. In this case, I change meter, 0.10 meter. Okay, for image distance here, image distance depends on this rule over here. If the image is on the same side as the reflected ray, then it will be positive. So let's see where is the reflected ray. Well, we know that this mirror here is an opaque object, so light can't really pass through it. Any light that strikes on this mirror will get reflected back to this portion of to this area over here. So we know that any reflected ray will appear in front of the mirror instead of the back of the mirror. There will be no reflected ray behind the mirror, only happens in front of the mirror. So if the reflected ray is here, then we find out that our image is also in front of the mirror. We can determine that the image is on the same side as the reflected rays. In that case, our V here should also be positive. Okay, what if your image is now produced at the back of a mirror? In that case, most probably a virtual image. Then your image is on the opposite side to the reflected ray. Remember, reflected ray always happens in front of the mirror. You can't let light ray pass through the mirror. So if your image is on the opposite side to the reflected ray, then you call your image distance to be negative. So let's say if I measure here 20 cm, then for this case, since I know my image is in the same side to the reflected ray, then my value here will be positive 20 cm, positive 0.20 meter. Okay, so you have to be very clear what is reflected ray, where is it, then is it at the same side with the image or not. Okay, so these are the characteristics of object, in this case represented in terms of distance. This is the characteristic of image, in this case represented in terms of the image distance. Now the characteristic of the mirror, which is represented by the center of curvature or the focal length of the mirror itself. Okay, so for focal length that we substitute in here, we need to be very sensitive whether it's positive or negative as well. So for positive, the center of curvature, which is this C over here, that controls this, that creates our sphere, that cuts out this mirror. Our center of curvature should be at the same side as the reflected rays. So if you see here, my reflected rays is in front of the mirror, and my center of curvature is also in front of the mirror. So since they are both on the same side, then our focal length for this case will be positive. Okay, if you happen to use a concave mirror will have a shape like this, right? Then your concave mirror, since your shape is like this, you know it's created by a sphere that is something like this. So you know that your center of curvature will be behind the concave mirror. The concave mirror is like this, but your center of curvature is behind the mirror. So in that case, your reflected ray, which is in front of the mirror, is at the opposite side of the center of curvature, which is behind the mirror. In that case, our convex mirror, you will get a negative f. Okay, so you can generalize this case here to be concave mirror, positive f, convex mirror, negative f. But I still teach you this method here because this method here is general. Later when you move on to lens, you don't need to remember another system. You just need to know that if the reflected ray is at the same side to the center of curvature, positive. Opposite side, negative. So this system here is general, so I hope you really can put it down in like record it in your mind. Okay, so that's how you determine whether u, v, and f should be positive or negative. We call this the sign convention for chapter 7. Okay, the next equation that I'm going to introduce here is the magnification. So magnification is represented by this symbol here, m, capital M, and it's a ratio between the h of the height of the image divided by the height of the object. So what does this magnification, what kind of meaning does this magnification means? Okay, you might heard before 2 times zoom, 5 times zoom, 10 times zoom. Well, that's magnification basically. Okay, if your image that you create is larger than the object itself, let's say you have a 1 meter ruler, but you create an image which is 2 meter, then effectively you are enlarging the image, right? You are magnifying the image. So you get the m, which is 2 divided by 1, then you get a magnification of 2. So using this mirror, if you place the object at this particular distance, your image should have a magnification of 2 times compared to the object. So that's the idea. So the distance is also the same concept, similar to this, just that the image is always on top, the object is always below. Okay, so let's try and talk about when the value of magnification is like this, what does it mean? Okay, so magnification can be any value ranging from negative infinity to infinity, actually any value. Okay, but we can split into a few range. Let's say if we are interested in whether the object size is getting larger or getting smaller, then we're looking at whether it's magnified, same size, or diminished, right? So to determine this using magnification, if you happen to see that your m here is greater than 1, then it means that your h image will be greater than h object, right? So if h image is greater than h object, it means that the image is larger than the object, so you can rightfully say that it's magnified. Okay, so if it's between 1 and 0, then it'll be 0 point something, right? So 0 point something is actually a fraction which the upper part will be smaller than the lower part. Let's say like 0.8, right? 0.8 is 8 over 10, right? 8 is smaller, 10 is larger. So what I'm trying to say is that h object will be larger than h image if your range of your magnification is within here, 0 and 1. The same thing over here, if your range is 0 to negative 1, it's still between 0 and 1. The absolute value is still between 0 and 1. It still carry the same meaning. Your object here is still larger than your image. But the only difference caused by the negative sign is now your image is inverted. So your image might be below the optic axis, while your object is above the optic axis. So the orientation is flipped already if you enter the negative region. So if your magnification is negative value, then it means your image is flipped already. Okay, no matter whether it's between 0 and negative 1 or more than even less than negative 1. As long as your value go below 0, then your image will be inverted. Because the negative sign is caused by your image here being, let's say your object here is upright, right? Then your image here, if you put a negative sign, then it means the image is below the optic axis. Okay, hi here is measured with respect to the optic axis. So if you go below the optic axis, your hi should be negative. If you go above the optic axis, then your h should be positive. So in this case, you can see that h object here is positive, h image here is negative. And if one is positive, one is negative, then you get the idea that the M will be negative, which means that it's an inverted image. Okay, so if you move on, if we have absolute value, if we have absolute value that is more than 1, in this case this range over here, the absolute value more than 1, then we can say that the object is again now magnified, because the value of hi is greater than ho if we just ignore the sign. Hi is greater than ho, so it means it's magnified. The negative sign carries the meaning that it's being inverted. Okay, so that's the idea of magnification when we talk about object image height. If you talk about it in terms of distance, then there's a negative sign in front. Okay, let's try to put it into an example. Let's say in this situation over here, we can see that the reflected ray and the image are on the same side. In this case, our V is positive. So if our V is positive and our U is positive, then you'll find that the magnification will be a negative value, because positive divided by positive is positive, multiplied by a negative sign, it becomes a negative value. So what does this negative value mean? It means it's inverted, which is true. If your image is formed on the same side as the object, it should be on the opposite side of the optic axis, making it inverted. So everything makes sense. You just need some time to figure everything out. Okay, so that's how you use the mirror equation and the magnification.